Alright, so think back to when we first looked at this topic. I showed you this diagram here of some field and asked you to describe to me, what do you guys see? I think I heard one of you guys say that it looked like some carpet, and it does look like a pattern that's just kind of repeating itself. It turns out that we realized this was actually a farm, and that's how they irrigate their fields, because it's the most efficient way to do it. Something called center point irrigation, where they have this kind of point, and they have some kind of machine that looks like this guy here, and it's going around the field. Okay, and we realized this is the perfect description of what we call a locus, a single point that has to meet some criteria or some movement. And we realized for a circle was when we had a fixed distance from a point. So back to that example, it was just going to be however long our irrigation machine is, and that's the restriction on its path. I can only go around in that direction. So let's look at this mathematically. Now, we've looked at locus for quite a while, so hopefully we're pretty comfortable with it. So we've got a question here. Find the equation of a locus of a point that is always 2 units from the point a minus 1, 0. And I've got my point here, a minus 1, 0. And I could see, for example, one point that would fit that criteria. So 2 units away would be this guy here, or I could have this guy here, or this guy up there, and some guy down here. I can't fit my screen. But then we also realized that this point is actually variable, right? It could occur not only in these 4 spots, but I could actually have points that are, for example, here, or here, and here and here. And then when I connected them all up, I actually got a circle that was happening around this point as my center. A was my center. So, in order to start this question, we always realize that whenever they say the locus of a point, we can always set up that variable as p x, y, okay? Because we know that those variables are always changing. The next thing I realized is, hang on, the distance PA actually has a condition. And that condition is that PA always has to equal 2, okay? But then, as we were doing locus, we realized that we used the distance formula. D is equal to the square root of x2 minus x1 all squared plus y2 minus y1 all squared. But that got kind of finicky because every time we had to work with the square root. Instead, we skipped straight to the step where we square both sides because that removes this square root symbol. Okay? So I know I want to find the distance PA, and I know that has to equal 2. That's my condition. But instead of having to write the square root, I can just say, by squaring both sides, I'll get PA squared. Remember, PA is a single value, so it's kind of like a distance, equals to 2 squared, or PA squared equals to 4. From there now, I can skip straight to substituting this part of this formula, the part inside the square root. So I know I've got the point a minus 1, 0, and p of x of y. So all I have to do is say, alright, well, let's subtract the x coordinates, that's this part here. So I've got x minus 1 all squared, plus, and then I subtract the y coordinates. So I've got y minus 0 all squared. And that has to equal to 4, because I squared both sides. And then I can just simplify this out. I've got x plus 1 all squared plus y squared equals to 4. And if you remember from, I think, chapter 3 or 4, we were looking at the different functions that we have. And this actually perfectly describes a circle. But not just any circle. A circle with center minus 1, 0, radius equals to 2. And if I graph that function over here, x plus 1 all squared plus y squared equals to 4, that's exactly what you get over here. And you can see, I was a little bit off with these points, but that's how we can describe the movement of all the points that satisfy that condition over there. And that's what we create. We create the circle shape. Okay?